So now we're going to get into a special case of using Newton's second law. You know, we've been using Newton's second law for a while, but now we're getting into using Newton's second law for circular motion. And the basic idea of circular motion comes from the acceleration stuff we've been doing in labs. So if you have an object that's moving in a circular path, here's the center of the circular motion. Let's say that we're interested in what's happening at this point. And say the thing is going this way, and let's say it's slowing down. Then this is all stuff that you have done before. What's the direction of the velocity vector at this point? If this circle is the path that the thing travels, then tangent to the path is this way. And so the velocity is this way. That's tangent to the path in the direction of motion. Okay. Since it's slowing down, which way is the parallel part of the acceleration? In the opposite direction of the velocity. So I'll call that a parallel. And then the perpendicular part of the acceleration always goes toward the center of the circle. So here's your a perpendicular. In lab, then, what we say is, okay, the total acceleration is somewhere in between those two green directions. But mathematically, if we have numbers for those, and we're trying to calculate the total acceleration is the sum of those two parts. Okay? And so, you know, that's the most complicated stuff that has to do with circular motion. And hopefully that already feels pretty comfortable. So what's new in doing calculations with circular motion? There are only 3 new things. So there are only 3 new things for circular motion. And 2 of those 3 are just new names for stuff. Okay, so the first one of these is, both of these just have to do with the names for the parts of the acceleration. We've called them a parallel and a perpendicular. But specifically when you're talking about circular motion, for circular motion, what we normally call the parallel part of the acceleration part that's parallel to the velocity, for a circular motion, that's called tangential acceleration. And I'll just denote that A sub tan. And notice why that name makes sense. The part of the the velocity is always tangent to the path of an object. And so anything parallel to it is always tangent to the path of the object. So it makes sense that you would think of this as like tangential to the path. Okay? The second new thing is also just naming, and it's a new name that we're going to call the perpendicular part of the acceleration. So for circular motion only, a perpendicular is called the centripetal acceleration. And I'll call that A sub sen. Okay. If it was my choice, I would have called everything tangential acceleration and maybe everything centripetal acceleration, no matter what kind of motion it is. But people only use these terms for circular motion, so I kind of have to do what everyone does. But the idea is exactly the same as the parallel part and the perpendicular part of the acceleration. And then the only new thing that that isn't just a naming thing for circular motion is that the magnitude of the centripetal acceleration is always the speed squared divided by the radius of the circle. So this capital V is the speed. This R is the radius of the circular path. Okay. Well, this is kind of an amazing fact. I mean, you certainly don't know this for any other type of motion. Basically what this says is if you want an object to keep turning in the particular way that keeps you in a circular path, this is how much you have to accelerate toward the center to keep turning that amount. Okay, it doesn't work for any other type of motion, but it works if you're in along a circular path. And that's really all of the new stuff. I have one sort of philosophical kind of question. Circular motion is it's like the only shape of motion that we're going to work on specifically. So why do we care about circular motion? Like, why aren't we doing square motion and elliptical motion and all these things? Why do we care about a circular path? The answer really comes from the motion of rigid bodies. So, like, why do we care so much about circular motion? Really, the answer is for any rigid body, rotating about a point, every point on that body follows a circular path. So like if you have let's say you have a board that is free to rotate around like a hinge or a pin at this point, and let's track the motion of a few points on this body. Any body you choose, and they don't all have to be on the center line like this. Let me pick one out here. every one of these points is in a circular path around that point. And so there's a natural connection between the motion of rigid bodies and circular motion. What are you doing? Okay. So there's a natural connection between the motion of rigid bodies and circular motion. We'll divide circular motion up into two different types. The first one is called uniform circular motion. And uniform circular motion is an object traveling around a circular path and the speed stays constant during the motion. And then everything else is called non-uniform circular motion. And that's where the speed changes. Okay, so if something's in uniform circular motion, what do we know about the acceleration directions? So if the speed isn't changing, uniform circular motion, the part of the acceleration that's, well, which one is going to be zero? The part that's parallel to the velocity or the part that's perpendicular? Parallel, yep. And so in uniform circular motion, the total acceleration is just the centripetal, right? Because the parallel is zero. The tangential is zero. For non-uniform circular motion, the tangential acceleration is not zero. And so to calculate the total acceleration, you have to add these two parts up. So what's the direction of the total acceleration for something that's in uniform circular motion? It always points toward the center of the circle. That's not true in non-uniform circular motion. Oh, and I didn't say this, but I said that tangential acceleration is a pretty sensible name for the part of acceleration that makes circular motion speed up. I didn't say anything about this. That's a word you haven't heard before, most likely, but it just means toward the center. So this makes a ton of sense too. Okay, so I'm going to give you a list of sort of general steps for doing circular motion problems. And then we'll go through a couple example problems. So these are general steps for circular motion problems. And later we're going to talk about a separate way to approach what I'm calling tetherball problems. Tetherball problems are problems where, I mean, it's like the tetherball game where you have something that's only contact is to a string that's swinging it in a horizontal circle. Okay, we'll approach those a little different. But everything that's not a tetherball problem, we're going to approach this way. So the first step is you need to identify a plane where this motion is happening. So you're going to choose a view for your calculations. And you're going to choose to be looking directly at the plane of the motion. So choose a view for the calculations where the circular path is visible. Okay, so for example, if you want to do if you have this toy train that's traveling along a track on the floor, you don't want to take a view from the side like this. You want to think of it from above or below. Let's say this is a view from above. And so the train is here, and it's going this way. If you don't choose to do the problem from a perspective where you can see that shape as a circle, then it's going to make everything a lot harder. This also, when you choose this view, you're also choosing where your coordinate system is going to be. So once you choose your view, you know, your coordinate system exists in that plane. Second, choose the point on the circular path to analyze. Sometimes you'll be told what instant to look at. Sometimes you just can choose for yourself. So once you've chosen the view, the orientation of the coordinate system, then let's say we're going to do a calculation involving that point. Third, draw a vector that's tangent to the path in the direction of motion. That's the velocity vector. So there's the path. Let's say this is still the same motion, so we're talking about from above a counterclockwise motion. That's the point we're trying to analyze. So I'm going to draw a vector tangent to the path in the direction of motion. That's the velocity vector. Third, draw a vector pointing from the point of interest toward the center of the circle. That's the centripetal acceleration. Okay, so this is what we have so far. Now the centripetal acceleration goes from this point toward the center. The magnitude of this, the magnitude of a centripetal is v squared over r. So you can use that to calculate the components of that vector. In this example, I'm using a standard coordinate system, so the centripetal acceleration vector is pointing in the negative x direction. And so just for this example, the centripetal acceleration is negative v squared over r for the x component and 0 for the y component. Fourth, you only have to do this one if it's non-uniform circular motion. But if it's non-uniform circular motion, draw the tangential acceleration vector if this object is speeding up, then velocity and the tangential acceleration are in the same direction. And if it's slowing down, the velocity and the tangential acceleration are in opposite directions. Now, at this point, you're basically done with the analysis of the circular motion. Now we're going back to stuff that you're very familiar with. I guess first of all, the total acceleration is just the sum of the two parts. Then draw a free body diagram of the object, and then use Newton's second law. And really every problem is going to flow this way until we get to tetherball stuff that I just have an easier approach for. Anybody have any questions about the approach or the meanings of any of these things? So just remember, if you're dealing with circular motion, you don't call it aparallel and aperpendicular. It's the same two things, but you call them tangential acceleration and centripetal acceleration. And then the magnitude of the centripetal acceleration, really the big news about this is that it's always equal to the speed squared divided by the radius of the path. Okay, so let's do our first example problem. Let's say that there's like a airplane. Looks like a fish, but. Okay, and say it's going through, following this circular path. The center of this circular path to the path has a radius of 250 meters. And first, let's say if the plane has a constant speed of 120 meters per second, what's the acceleration of the pilot at the point P here? And then let's calculate the net force on the pilot. Let's instead calculate the force applied to the pilot by the back of the chair and the force applied by the seat of the chair. So by the push of the back of the chair and the push of the seat of the chair. Okay, so we'll go through this one and then we'll do a sort of similar one. I need to give you the mass of the pilot. Let's say the mass is 100 kilograms. Okay, is this uniform or non-uniform circular motion? Uniform because the speed is constant. So let's just start going through the steps. So here's the circular path. I'm going to use a coordinate system like this. Now we need to choose a point on this circular path to do the calculation for. And in this problem, we're actually given that we have to do it here. Okay. It's following a path like that, counterclockwise. So the velocity vector is tangent to the path in the direction of motion. So there's the velocity. Now the centripetal acceleration is from the point toward the center. So that blue vector is acentripetal. The magnitude of acentripetal I'll just write that as a centripetal without the vector sign over it. So this is the magnitude, is equal to v squared over r, which is 120 squared over 250. The radius is that 250 meters. The speed is 120. And this comes out to be 57.6. What are the units? Yep, this is a type of acceleration, so it has acceleration units, meters per second squared. And now if we want to put this in a vector form, you can see that that blue vector is in the negative x direction. So the centripetal acceleration is negative 57.6 for x, 0 for y. Okay, we already figured out this is uniform circular motion. So the total acceleration is the centripetal plus the tangential, but we don't have any tangential in this problem. So the total acceleration is negative 57.60. Is that a lot of acceleration or not much? Do you have a feel for that? Well, a lot of times when people are talking about aviation-related stuff, they talk about accelerations in terms of numbers of g's. A single g is 9.81, so this is somewhere around 6 g's of acceleration, which is a lot, but people do that. Pilots do that for short amounts of time, and it's not a problem. So now we figured out the acceleration. That's part A. Now we want to calculate the force that's applied to the pilot by the back of the chair and the seat of the chair. So let's think about at this instant, well, at this instant, what direction is the plane moving? The plane is moving, the nose of the plane is in the direction of that velocity vector, so it's just going straight up at that point. Okay? And so the pilot, if you draw a free body diagram of the pilot, it would look something like this. Okay? And let's think about the forces that are acting on the pilot. There's a weight force down. Make it look straight. And that is the mass times 9.81, so 981 newtons down. Then there's a pushing force from the seat, from the back of the seat. I'll call that NB for back. And then there's a pushing force from the seat. I'll call that NS for seat. And now we've dealt with all the contact forces. So now we can go to Newton's second law. That NB is in the positive y direction. NS is in the negative x direction. The weight is in the negative y direction. And this is equal to the mass times the acceleration that we already figured out. So the x equation says negative n seat is equal to negative 5760. So ns is equal to 5760. This is a force, so that has to be in newtons. The y equation says NB minus 981 is equal to 0. So NB is equal to 981. So the seat is applying a force to the pilot of almost 6,000 newtons. And the back of the chair is applying a force of 981 newtons. Any questions about that? Okay, let me do an example. I'm going to use basically the same example, but this time the speed is going to be changing. It's going to be non-uniform circular motion. So this time, let's say that the plane so it's still going through this circular path. The radius of the motion is still 250 meters. And at the instant shown, the plane has a speed of 100 meters per second and is slowing down at a rate of 200 meters per second squared. So first, what's the acceleration of the pilot? And then second, calculate those same two forces, the normal force applied by the back of the chair and the normal force applied by the seat. Okay, so again, we're going to start by identifying a plane to calculate this motion in. It's always going to be a view where you're drawing, the first thing you're drawing is a circle. And I'm going to use this coordinate system, same as before. This time we're looking at this point down at the bottom. We're still assuming that the motion is this direction. So the velocity vector is tangent to the path in the direction of motion. The centripetal acceleration is from the point we're looking at toward the center. So there's the centripetal acceleration. The magnitude of the centripetal acceleration is the speed, this time it's 100 squared, divided by 250. And so this time we get a magnitude of 40. Now look at the picture you drew. This is acting in the positive y direction, so the total centripetal acceleration is 0, 40. Okay, in this one, do we have to worry about tangential acceleration? Yes, the speed is changing. It says it's slowing down, and so the tangential acceleration has to be opposite the velocity. So there's the tangential acceleration. We're given the magnitude of that tangential acceleration. So all we're using this picture for is to figure out the components. Tangential acceleration is in the negative x, and its magnitude is 200. So this is negative 200, 0. And so the total acceleration in this case is 0, 40 plus negative 200, 0. And that's negative 200, positive 40. Now that we have that, we can draw the free body diagram of the pilot. At this instant, at the bottom of that motion, the pilot's sitting upright like this. We have a downward force of 981, an upward pushing force in seat, and the back of the seat is pushing this way. One thing that's going to come up here is, well, we'll see it in a second, but this N for the back, N sub B, is going to come out to be negative, and we'll talk about what that means. But this is a complete free body diagram. Newton's second law says NB 0 plus 0 NS plus 0 negative 981 is equal to the mass times the acceleration The x equation says n sub b is equal to negative 20,000. This is Newton's. The y acceleration, or the y equation says n sub s minus 981 is equal to 4,000. So n from the seat is equal to 4,981 newtons. Okay, well, we got that normal force from the back of the chair is equal to negative. It's a negative value. What does that mean? It means that the direction is the opposite of what I have drawn here. Okay, so what that's saying is as the plane is slowing down, the horizontal force that has to be applied to this pilot is the restraints pushing in the negative x direction or pulling in the negative x direction. Okay, so this really would be the, pulling by the seat belt. Any questions about that example problem? Hopefully you'll just do enough of these that it starts to, you start to sort of naturally go through these steps, treat every problem the same way. Okay, so I'm going to do another example, but this time I'm going to give you a little time to work on each one of the steps, and I'll kind of walk you through it step by step, but just to get used to this idea. So let's say that there's like a metal pinball that's attached to a string. And let's say it's going around the circular path this way. The mass of the ball is 60 grams, 0.06 kilograms. The length of the string is 0.25 meters. Let's say 0.2 meters. And let's say that this is moving with a constant speed of 6 meters per second. What's the tension in the string? Okay, so the idea here is that this ball is being swung around by this string, but it's also in contact with the ground. It's like spinning around on a smooth table. So this is almost like what I describe as a tetherball problem, except that the ball is also in contact with the table. Okay. So first, choose a view for this problem. I tend to choose the top-down view, but you could do bottom-up view too. Draw the circular path in the view that you want and put the coordinate system in there. I'll give you a few seconds for that. Okay, so there's the circular path. And we'll use a coordinate system like this. Now we have to choose a point to analyze. Let's say we're going to choose this point. I'm just going to choose that for us, otherwise everyone will do this differently. Yep.
Can it be like any point on the circle we choose?
Yes, that's right. And I said let's all do the same points so that everybody's answers look the same. But no matter what point you chose for this problem, you'd get the same answer for the tension at the end. Okay, next, draw the velocity vector. So I'll give you a couple seconds to figure out the direction of the velocity at this end. Okay, so it's moving this way. And so the velocity is tangent to the path in the direction of motion. So there's the velocity. Now calculate the components of the centripetal acceleration vector. So you're going to draw that vector. You're going to calculate the magnitude of the vector, and then you're going to combine those two to get components. Okay, so centripetal goes from the point that we're looking at toward the center of the circle. So here's the centripetal acceleration vector. The magnitude of that vector is v squared over r, which is 6 meters per second squared divided by 0.2. And that comes out to 180 meters per second squared. From the picture, you can tell that's in the negative y direction. So the centripetal acceleration vector is 0, negative 180. Now, is there going to be a tangential acceleration or not for this one? No, because the speed is constant. And so this is equal to the total acceleration because there's no tangential. Okay, so now we're going to go to a free body diagram of the ball. And this is the first time you're going to see this. We haven't done stuff like this in this class yet. But there's some forces happening here from the view that we're taking that aren't going to show up in the equations or the free body diagram because they're out of the plane, either into the page or out of the page. So if this is the ball, like, there's always going to be a weight force acting on the object, right? But in this case, notice that the weight force is into the page. And so in a coordinate system where x goes to the right and y goes up, how would you ever add those up to come up with something that goes into the page or out of the page? It's just they don't relate to it at all. And so you can just leave anything that's perpendicular to your analysis completely out of the problem, okay? What you also see some people doing sometimes is they'll use a notation where something going away from you is a circle with an X on it, like you're looking at the feathers of an arrow, and something coming towards you is a circle with a point in the middle, like you're looking at the point. But I'd say just leave it off, okay? So if you leave off the weight force, and you leave off the normal force from the surface touching the ball, the only force that's left is the cable force acting this way. Do you see that? Anybody have any questions about that? And so now I'll go to Newton's second law. It looks sort of weird to have something that doesn't have any weight on it and has so little going on, but that's just because we're only looking at the forces that are in this plane. So the forces are 0, negative t, and that's equal to the mass times the acceleration. And so the y equation says negative t is equal to negative 10.8. And so T is equal to 10.8 newtons. So if you're doing this motion with a string that can withstand, say, 11 newtons of force, then it'll do this and it won't break. If it can only withstand 10 newtons of force, then you do this motion and the string will break. Okay? With me on that? Anybody have any questions about this one? Okay, well, okay, let's do one more. Let's do another one that's that has tangential acceleration. So another non-uniform circular motion. So this time, let's say you have a ball and a string again, and you're swinging it in a circle. And this circle is like vertical, so this direction is up. And let's say that the mass of that ball is 0.06 kilograms again. And let's say that at this point P, and by the way, it's going this way, so when it gets to P, it's on the way up. At P, the ball has a speed of 10 meters per second. And it's slowing down at 9.81 meters per second squared. If the string length again is 0.2 meters, what's the tension in the string at that point P? Okay, so start out again, draw the view where that circle is visible, and draw the coordinates. Okay, so this time our view is going to be just from the side. It's going to be the view that's drawn in that picture. And so our coordinate system is like this. And the point that we're interested in is this point here. So now draw it's moving around this circle counterclockwise, so the velocity is this way. Now find the components of the centripetal acceleration. Okay, well, the direction of the centripetal acceleration is from the point toward the center. The magnitude of the centripetal acceleration is the speed squared divided by the radius of the circle. So that's 10 squared divided by 0.2. So that's 500. We can see from the picture that the centripetal acceleration is in the negative x direction. So the components are negative 500, 0. Okay, next, this one there is a speed change, so we are going to have a tangential acceleration. So draw the direction of the tangential acceleration and then use what you're given to come up with the components of the tangential acceleration. All right, well, it says in the setup to the problem that it's slowing down at 9.81 meters per second squared. So if it's slowing down, the tangential is opposite the velocity. And now you can see that's in the negative y direction. And so the tangential acceleration is 0, negative 9.81. Now the total acceleration is the sum of those two parts. So that's negative 500 for x, negative 9.81 for y. And now we'll draw a free body diagram. Take a couple minutes and see if you can draw this free body diagram. Okay, so on the free body diagram, there's the ball. The weight force is down. That's 0.06 times 9.81, so that is 0.5886. And now the cable force. Remember, the cable pulling force is always parallel to the cable away from the body, so it's going to be this way. And now, write out Newton's second law using this free body diagram and that acceleration and calculate the value of that t. So the last step then, Newton's second law, the t is in the negative x direction. The weight is in the negative y direction. That's equal to the mass times the acceleration all we want is that t, so we can skip the y equation that just would come out to say 0 equals 0 anyways. And the x equation says negative t is equal to 0.06 times 500, so that is just 3, negative. And so the tension is 3 newtons. Oh, thank you. I was just like going through thinking like, does that make sense that it's smaller than last time? Okay, 30 newtons. Any questions about that? So that's basically circular motion. Next time I'll talk about how to do the one specific type of problem that you don't want to do this way. That's tetherball type problems. And then that's it. Okay, thanks.